Okay.
Yes.
So let me see it. Here is a horizon. The red, chain of line segments, you see it. This is a simple modeling of the horizon. And what we want to do is we want to find the optimal placement of telephone towers here or here or here or here or here or here. And we want to place the minimum number of towers so that the points on the horizon can be visible to the towers. Am I clear about the problem? Okay.
Yes.
Okay. So admit, so I have to do it. Now, why we say 2.5D terrain and why we say, okay, 1.5D terrain. 2.5D terrain is our surface of the earth. All the Google Maps and environmental data display and GIS, everything is done. So surface of the earth can be viewed geometrically like this. And many algorithms that have been developed on these things are very hard. In fact, they have been proved to be something called intractable. That is a term used in computer science, or NP-hard or intractable. That means nobody will be able to find a solution, optimal solution. So they go for approximate solution. And they also try to simplify the model. So this thing, if we make an intersection with the vertical plane, then we get this kind of things. And this is called 1.5 D terrain, which is an oversimplification of the real terrain, that is 2.5D terrain. We may be wondering, why are we saying 2.5D terrain? It is because as we go up in the mountain along the ridge or along the skyline, the visibility increases as we go up and up and up. That is why it is called 2.5D terrain. All right. Okay. So let's try to understand with a very, very simple structure. So we are given a 2.5D terrain, and we want to find a set of guards or points from where we can see the whole of terrain. In this example, if you place one tower here or one illumination point, well, some of them are visible, but this one over here and this one over here are not visible. So this is trying to show you that if we do not place it in the right place, and if we do not have the right amount of tower, it will not be illuminated. So the problem is where to place and how many to place. Well, if we place everywhere, we will see it, but that is too expensive. So we want to cover the points by placing fewer number of towers. Okay. All right. Now, in this case, if we place 3 towers, one here, and one here, you can check it that every point is visible. So anybody with a cell phone over here can be connected if these 3 towers are there. Am I clear, guys? Any question?
No, you're clear.
Okay, very good. So this problem was started by Lee and Lee in 1986, long time back, actually. And then still this is having a lot of room to grow. And Lee and Lean actually proved this is an intractable problem. That means it's a very hard problem, not as a tower placement problem, but illuminating a room with minimum number of light bulbs. For example, in this case, if we put one guard here and one guard here, or one light bulb here and one light bulb here, everything can be seen. Okay. Now, we model the problem as a very simple room in which the base is one big line segment, and then upper part is a monotone chain. See, this is a monotone chain. So when we model a room by a monotone polygon, rather X monotone polygon, then it precisely captures the problem that is faced for placing telephone towers on 1.5D terrain. So you can think this as 1.5D terrain, and this is the base. And these two researchers from Germany, King and Kron, in 2011, they said that even when we simplify, make an oversimplification like this problem remained intractable. Those of you who are not in this computer science area, intractable means very, very hard problem, and most probably nobody would be able to find an optimal solution for that one. So this problem becomes a nasty even when we make an oversimplification. Okay. Then people come with one-sided guard and two-sided guard, or one-sided tower and two-sided tower. So one-sided tower, any point can be guarded by any guard. So this point can be guarded by here or here. Now two-sided guard, just a second. Two-sided guard is, just a second, I cannot somehow, okay, let me see. Okay, here it is, okay. So two-sided guard is any point has to be visible to one over here and one over here. The motivation is if one of the tower is not working, still there is a probability of high connectivity. So that is why in this case, if we place towers like 1, 2, 3, 4, 5, then even if some of the tower go wrong, still connectivity will be there. So that is the motivation for having two-sided guarding. And it was introduced by Lai and Xiang in 2018. All right. Okay. So some of our students are working to develop some approximations algorithm. One is called greedy ranking. This was done in 2019. There is a lot of things to be done yet by one of my students, Katiwada. Another is greedy forward marching algorithm. Some progress has been made, and we will make some presentation of the progress made by my students in this area. Okay.
Yeah, Dr. Gewali, I just want to be mindful too of the time, because I don't know if they're going to cut us off at 2:15, but
Okay.
we have all the rest of the presentations to go through. Also.
That's fine. That's fine. How much time we are left?
It's now 1:20. Well, it's out there. It's 10:23.
Oh, and
So-
so we are supposed to be done by 10:25, or I'm already out.
Well, I think we have to go. I think every presentation was supposed to have about 15 minutes. So we have to
Okay,
get
then
through the
let's
rest of
do
the
like this.
presentations.
Okay, I think I was at least able to present what the problem is, and some of you who have interest, you can send email to me. I can send you the PowerPoints, or I can send you some of the prior work that has been done in this area, or some of the thesis and dissertation. Some of my students have done it, So at this point, I would just stop it and then ask for any questions the audience have.